All right, so again, welcome back from the weekend. The plan for today is to start in the chapter 4. We're talking about functions of several variables. Note the difference between this and chapter 13, vector functions, where the output was multiple variables. Here we're dealing with functions where the input is multiple variables. And we're going to kind of follow the book a little bit strangely here. We're going to jump from 14.1 straight to 14.3 in today's lecture to get started on partial derivatives. And in Wednesday's class, we're going to pick up with partial derivatives. We should finish it up on Wednesday and talk about tangent planes and linear approximations. We might get through all of that on Wednesday's class, or we might bump a little bit of 14.4 to a supplement. The planned supplement for this week is 14.2, limits and continuity. And if you remember kind of from Calc 1, the ideas of limits and continuity obviously underlie the ideas of derivatives. But it turns out that in functions of several variables, some of these ideas of limits and continuity are rather technical. So we're going to leave those to a supplement, and we're going to focus on really the most important points for moving forward, which is 14.1, 3, and 4. And then 14.2 will be in that supplement. Okay, so moving into 14.1, functions of several variables. A function of several variables, as I say here, is a function where the domain, the inputs, are a subset of Rn, and the range a subset of R. So we have multiple variables as inputs, a single variable as the output. And as I mentioned here, we'll primarily be concerned with the cases n equals 2 and n equals 3. Some of the material we'll discuss does kind of generalize to larger n. Some of it becomes a bit more difficult when we try to generalize to larger n. So we'll focus on the cases n equals 2 and n equals 3, and we'll actually treat them somewhat separately. And I think we'll see the reason for that coming up here pretty soon. So for example, we might say that a function taking R3 to R is a function of several variables because it has several inputs. It has maybe X, Y, and Z as inputs. You can almost even think of it as like a vector as the input, or certainly a point in three-dimensional space as the input, and the output being just a single variable, just a single number. And just a note here on notation as well, this function's output is just a real number. It's just a scalar. So we don't represent f as a vector. We don't represent it as like bold f or as f with a vector arrow above it as we did in chapter 13. I know that some of the stuff between 13 and 14, whether we have multiple inputs or multiple outputs, might be a little easy to get confused or to get mixed up between them, but it is important to keep the ideas separate. So we'll be careful to use the correct notation here in this chapter as well as chapter 13, just so that we're very clear. If we see a function f that is in vector notation, we know that it's a vector value function, has multiple outputs. If we see a function f just kind of as a normal letter, not bolded or with an arrow above it, we know that it has a single output. So this is an example I gave last time. We can consider the function f of x, y, z equals x plus y minus z. And we could plug in, for instance, the coordinate x equals 1, y equals 2, z equals 3. F of 1, 2, 3 equals 1 plus 2 minus 3 is 0. Again, we get out a scalar, a real number. We call this a function of several variables. More than one input, just one output. We could also look at an example like this one, g of xy equals x to the power y. And again, we could think of two inputs, maybe e and pi, for instance, x equals e, y equals pi. That's a point in two-dimensional space. And we see that the output is e to the pi, a real number. Maybe it's kind of a complicated real number, not a very nice one to deal with, but a real number nonetheless. It's not a vector as the output. Okay, so let's start by looking at functions of two variables where we have two inputs and one output. And we know that a function, it takes as inputs points in its domain and gives us outputs points in the range. So let's take a look at each of these functions and determine the domain. And of course, just like with kind of standard functions in a sense, with one variable input and one variable output functions, we could state the domain explicitly if we wanted to restrict the domain. And if we don't explicitly state the domain is taken to be all inputs that are valid, that give a valid output. So I see that I have the natural log of 9 minus x squared minus y squared. And I know that I can only plug positive numbers into the natural log. I cannot plug negative numbers, and I cannot plug 0 into the natural log. So I know the inputs to natural log have to be strictly positive. So for my domain, I know that 9 minus x squared minus y squared has to be strictly bigger than 0 to be a valid input for the logarithm. But this tells me that x squared plus y squared has to be strictly less than 9, or in other words, strictly less than 3 squared. Well, I know this boundary is going to be a circle of radius 3 in the xy plane. Remember, the xy plane here is not representing one input and one output, but it's representing a pair, an ordered pair of 2 inputs. And then the output would be something else. So I know that my boundary is a circle of radius 3. I also know by my strict inequality that I do not want to include my boundary, so I'm going to draw it with a dashed line. I can almost guarantee that at some point today I want to draw something as a dashed line. I'll draw it as a solid line, and then probably realize it 2 minutes later and have to go back and fix it. So but we don't want to include the boundary, and we know that we want the interior of the circle, which we can see, for instance, by saying that the origin is a solution to 0 squared plus 0 squared is less than 3 squared. So we want the interior of this circle of radius 3. And this would be a sketch of our domain. That would be a sketch of our domain. This would be more of an algebraic representation of our domain. And if we wanted to kind of just not very accurately represent what this function is doing, just kind of a sketch of what's happening. Over here we have the real line, and we have our range, our output space, and we're taking points from this input space and mapping them to points on this real line. And I'm not being super careful about whether these are in the correct order or not, but again, just kind of a schematic diagram of what's kind of happening. So this green kind of filled in circle here, this green disk, not including its boundary, that represents the inputs, and this red line on the right represents at least some of the outputs, or where the outputs would lie on this real line. Okay, so what about part B here? Well, I see that my function of x and y is square root of y over 1 minus x squared. So I see I have 2 potential problem points. I can't square root a negative number. Note that I can square root 0 just fine. Square root of 0 is just 0. So we can include y equals 0. That's not a problem. If we had 1 over root y, that might be a problem. Or if we had natural log of y, we wouldn't want to plug a 0 in there either. But square root of y in the top, we can include 0. So I need y bigger than or equal to 0. That's the only potential problem that I see for y. And for x, well, I can't have a denominator of 0. So when is 1 minus x squared equals 0? Well, that's whenever x is plus or minus 1, and I do not want to include those in my domain. So these are my 2 restrictions for my domain. And so again, I'm looking for y's bigger than or equal to 0. So including the x-axis, except at -1 or +1. All of the positive y's, but not including these two kind of half vertical lines. So this bit over here is all good. This bit is all good. And over here, as well as anything on the x-axis that's not ±1. And again, we think of this as being our domain. This is where we're getting our inputs into the function. And our outputs, we're imagining, are being mapped onto the real line over here, kind of like this. Again, this is just the schematic. I'm not being careful about which x's and y's I'm choosing as inputs and whether they're, what side of the other ones that they should be on. Just the schematic representation here. Any questions on functions of two variables to this point? I know we're taking a bit of time on this, but I do want to really drive home the differences between chapter 13 and chapter 14. I think it's easy to get the two kind of mixed up or to get some ideas conflated between the two of them. Okay, so what if I want to graph a function of two variables? What if I want to see more clearly the representation of the relationship between the domain and the range? That's really kind of what a graph is, right? As this point in the domain goes to which point in the range, but making that a bit clearer. I see that my domain is two-dimensional already, and then I have a one-dimensional range. I have kind of a total of 3 dimensions I need to represent. So for a function of two variables, I have two inputs, x and y, and then I'll label the output as maybe another variable, z. So I can think of each input, x, y, being associated with an output, z. That gives me an ordered triple. That gives me a point in 3-dimensional space. And because the pictures from the book are much better than what I can draw by hand, I just kind of grab the picture from the book here. So again, in our xy plane, we have this domain, this kind of orange colored blob down here. And then for each point in the domain, we have an output. For each xy input, we have a real number output that represents the height above that domain. That's our z. So this blue surface here, this kind of curved surface that exists above our two-dimensional domain, is the 3-dimensional graphical representation of our function. Putting in inputs in the xy plane, or the subset of the xy plane, yields outputs that lie on this blue surface. And you might be anticipating a little bit what the problem, or maybe not problem, but what some of the challenges are with functions of 3 variables with 3 inputs. Well, if we have 3 inputs, we would need a 4th dimension for outputs, and that's not going to be super easy to represent graphically, right? We've kind of already used up all 3 of our easy graphical dimensions just with functions of 2 variables with 2 inputs, as we need to use one of those dimensions for the output. And as a side note, the function z equals ax plus by plus d, or in other words, alpha x plus beta y plus gamma z plus delta equals 0, where we're thinking of z as the height being our output, is an arbitrary linear function in R3, and we see clearly that it's a plane. This kind of rearrangement makes it very clear that this is a plane in 3-dimensional space. That might not have been so clear from this representation over here, but just rearranging things, basically putting the z on the right-hand side, and in this case, taking gamma to just be -1, we see that this arbitrary linear function, where we see the independent variables only coming in linearly, x to the first and y to the first, no x squared or y squared, no x times y terms either. We see that's a plane. And we'll see that planes are quite important throughout this course. So we'll be taking a look at that later on in chapter 14. Okay, let's look at an example. Let's try to sketch the graph of f of xy equals square root of 4 minus x squared minus y squared. Now, again, we tend to label the output as z and the inputs as x and y. So I see that z equals root 4 minus x squared minus y squared. I know that z is bigger than or equal to 0. And I see I can square both sides. I can get all my variables on one side. And I see I have x squared plus y squared plus z squared equals 2 squared. Or this is just the equation for a sphere of radius 2. I can see that by square rooting both sides. And I see that the length from the origin to any point x, y, z that satisfies this, this original equation up here, the length from the origin to any point has to be 2. So constant length in 3 dimensions, that's a sphere. And along with z being greater than or equal to 0, because we took the positive square root here for our function, that tells us that we have the upper half sphere. And this is going to be of radius 2. So I'll start by drawing a circle of radius 2 in the xy plane, just looking at what happens when z is 0. When z is 0, x squared plus y squared equals 2 squared, circle of radius 2 in the xy plane. And then I have kind of this dome going up and over here and coming this way as well. So I just have my upper half sphere of radius 2. Now note that when I say sphere, that's just a surface, right? This isn't like a filled in solid. This is like if we turned it upside down, it would look like a cup. It's, open in the middle. It's just this surface here. Okay, let's look at another example. Example 3 here, a little bit more involved. Let's let T of xy be the temperature in a 10-foot by 10-foot room on a winter night. So we're thinking that kind of the tendency is for the room to want to be cold. We have one corner at the point 0, 0, the other corner at the point 10, 10. And in this room, we have a temperature function. So if we're standing at a certain point in the room with a little instant read thermometer, the temperature would read according to this function based on the x and y coordinate that we're standing at in the room. Okay, so first off, let's just get an idea of our domain. I mean, it's not super complicated, but just to put it out there, what it is. So our domain is just this 10 by 10 square, right? These are the inputs that we're going to be choosing. This is where we're going to be, standing with our thermometer and reading the temperature at that point in the room. So that's x and this is y. So what does our temperature function represent? Well, it represents my reading at each point in the room. So I'm thinking of this room as very two-dimensional. I'm thinking that if I'm closer to the ceiling or closer to the floor, the reading is the same. It only depends on x and y, not on my height. What the third variable is representing is the temperature at each xy location in the room. Okay, so I'm actually going to draw my axes kind of like we've been drawing them. X, Y, and T in this case. So things have flipped around just a little bit. I know that my domain, maybe I'll draw it in blue. My domain is this 10 by 10 box. And then I want a graphical representation of my temperature. So I want the surface above this domain, similar to this up here. I guess maybe I should have drawn the domain in red and the surface in blue to be consistent with the colors, but I don't think that's such a big deal here. Well, I'm going to look for some kind of easy to describe behavior. I do see that when y equals 5, this y term actually goes away and doesn't really have any influence, and I get something that looks like downward opening quadratic in x. So the temperature looks like more or less minus x squared when y is 5. So along this line in the domain, I have a temperature that looks, say, more or less something like minus x squared. I mean 78 minus 1/10 x squared, but it looks something like this. Oh, let me switch colors. Looks something like this. So I'm imagining this green curve that I just drew as being directly above that line y equals 5 for x going from 0 to 10. And that's representing kind of the temperature as the temperature reading as I, stand at this point, x equals 0, y equals 5, and kind of walk parallel to that x wall. Parallel, staying at y equals 5 and walking from x equals 0 to x equals 10. That's the reading I would get. Now, if y is a bigger number, say like 10, or a smaller number, say like 0, well, 10 minus 5 squared or 0 minus 5 squared, that's going to give me a larger number here. So as y deviates from 5, this y minus 5 squared increases. But note that it's hit by a minus, so the total temperature would decrease as I move as I'm looking at the picture, left to right, as I move from y equals 5 to y equals 10, or from y equals 5 to y equals 0, staying roughly in the same x value, my temperature is going to decrease in either direction. So as I come over here to say y equals 10 and I follow this line, I see that I'm going to have a lower temperature. But again, it's going to follow kind of that similar trajectory with respect to x as I walk along from x equals 0, y equals 10, this point here, to 10, 10, this point here. So it has that same kind of downward opening quadratic shape for the going along in the x direction, but just the whole thing is a little bit shorter. And then same kind of thing down here. At 0, 0, I start with a temperature that is lower than at 0, 5. Again, because this y minus 5 squared gets hit with a negative. So the more I deviate from 5, the lower the temperature ends up being. But as long as I stay at y equals 0 and walk from, say, x equals 0 to x equals 10, again, I follow that kind of, downward quadratic trajectory from the contribution from this x, this kind of minus x squared feel. So again, if I imagine myself kind of starting at x equals 0 and y equals a number, and then changing x, I get curves that look like these green ones, for instance. What if I did this the other way? I'm going to use a second color here just to kind of demonstrate it, but normally I would use the same color for all of these. But just to try to make it clear which lines and which curves are going in which directions, I'm going to use red to say, okay, if I started at 0, 0, and if I stayed at x equals 0 and progressed from y equals 0 to y equals 5 to y equals 10, what happens? Well, the temperature increases and then decreases, right? When x is 0, this term goes away. And again, this looks like a negative quadratic opening down, but here the vertex is going to be at y equals 5. That's going to be the highest point, and we're going down as we get lower values of y below 5 or higher values above 5 when x is 0. And similarly, say when x is 2 or 5 or 7 or something like that, we get a similar kind of behavior. And also when x is 10, we also get a similar behavior. So sometimes the way that I can get these graphs of surfaces and make them look pretty decent. I mean, I think this conveys the idea pretty reasonably well what's going on. I mean, I'm not an artist by any stretch of the imagination, but I think this does a decent enough job. Let me thin up this line just a little bit. I think that actually makes it look quite a bit better. So what we can do is we can isolate one variable. Say if I pick a number for this variable and then I move the other one, what is that curve going to look like? What is the curve going to look like, say, when I move parallel to the x-axis or parallel to the y-axis? And I see that this is going to be kind of a surface that has the highest point up here. That's kind of the peak of the mountain. And we go kind of down the mountain in the x direction, but also we go kind of down the mountain in either y direction as we deviate from 5. Or I'm going to try to do this. I'm hoping that it's not going to just blow up on me. I'm going to try to draw it the other way. We'll see how good my artistic skills are here. I'm going to try to draw it the other way so that we can see it kind of from the back side. So again, here's my domain. These are my inputs. And then moving along x, well, let me start with this curve at the very back here along the y-axis. That is a curve that looks something like this. And then for a higher value of x, we're a little bit lower, but we still, as we move along the y direction, we still have this quadratic opening down kind of feel. So this curve is like further into the screen. This is above, say x equals 5. And then further into the screen, we have a similar curve that's above, say x equals 10. And then we have these kind of quadratic curves going downwards like this. I think this is probably an easier representation to see kind of from the top. Again, I'm not a super great artist, but this is going to be our apex above x equals 5, x equals 0, y equals 5. So the highest temperature is at x equals 0, y equals 5, and then the temperature decreases quadratically, basically in all directions going out from there. Okay, so if we had to guess where the heat vent or vents are located, where might we guess? Well, I see that there's one very clear maximum, and the temperature decreases everywhere. The vents are giving out heat, and it's a winter night, so the room kind of wants to tend toward being cold. So we see that the one vent is pretty clearly at xy equals 0, 5 at this kind of single point of maximum temperature here. I don't see a surface that has like a high point at, say, x equals 0, y equals 5, and also another like high point at, say, x equals 10, y equals 5. Like maybe if I had something like a what is it, hyperbolic paraboloid or whatever, basically like a saddle, then I might think that maybe there's 2 heat vents at, say, opposite ends of the room. But in this case, it's pretty clear that the temperature just goes down in every direction we go. So it's pretty clear that I think there's one heat vent and it's at 0.5. And then C, if we want to sleep with a temperature of 70 degrees or less, where would we put the bed? I mean, it's maybe a little bit of a silly question, like, there are many other constraints on where to put a bed, like where are all the doors and the windows and all of that, but just, humoring the problem. In other words, what parts of the domain yield an output, yield a temperature of 70 degrees or less? What is this question asking? There's a couple ways I can think about it. One is just very, kind of sledgehammer approach, just figure out when is big T less than or equal to 70. There's also kind of a geometric approach. I've kind of run out of color, so I'm going to reuse the color blue. And I see that my temperature axis here, well, I know that when X is 0 and Y is 5 at the maximum here, my temperature is 78. So this is 78. And I know that as I plug in larger values of X or values of Y that deviate more from 5, the temperature goes down. So if I have X equals 10 down here, and let's say Y equals 10 as well, so then I have 78 minus 1/10 times 10 squared plus 5 squared. So this is 125 over 10 is like 12 and a half. So this is like 66 or something like that degrees. So I see that this height or this height is like maybe 66-ish. So what am I really asking? I'm asking, when does my function have height 70 or less? This is a nice kind of monotone function. As I move in a given direction locally, it just kind of keeps going in that direction. It's a little bit bad to call it a monotone function, but at least for the left half or the right half of the y's, it maybe is. So if I'm looking for a temperature of 70 or less, I'm asking, when is the height of the surface 70 or less? In other words, if I imagined a plane parallel to the xy plane at height t equals 70, I see that this plane is gonna, let me redraw it. If I have a plane here at height 70, and let's say that it looks like this, it needs to be a little bit higher. When I drew it, it wasn't really parallel to the plane below it. I see that this plane is going to intersect this surface something like this. So I see kind of in these corners, I'm going to be good. Kind of in the middle here, I'm not going to be good. That temperature is going to be too high. That's above the plane in the middle there. What exactly does that intersection look like of the plane with the surface? Or in other words, what does t less than or equal to 70 look like? Well, that's 78 minus 1/10 times x squared plus y minus 5 squared less than or equal to 70. Let's just do equals 70. And then we'll just use kind of common sense or an argument from this geometric picture up here for which side we should be on. So I see I can subtract the 1/10 times stuff over, subtract the 70 over, I get 8 times 10 is x squared plus y minus 5 squared. I do not need that first parentheses. Or I see that this is a circle with radius of root 80 or about 9. Root 81 would be 9, so this is just a touch less than 9. And center xy equals the x coordinate in the center is 0, the y coordinate is 5. And so again, I'll look at my domain, at my xy, at my layout of the room. I'm only interested in this box 0 to 10 on each axis. I'm looking for a circle with center at 0, 5. Oops, wrong axis, x equals 0, y equals 5. And radius of roughly 9. So going directly to the right, this may be around here, would be a point on the circle. And then as I rotate around, I should get a circular arc that maybe looks something like this. Now, if I want the temperature to be less than or equal to 70, should I be closer to 0, 5 or further away? Should I be more up here or more down here? Well, of course, further away. Either I can think of it as further away from the heat vent, kind of common sense. I can think of it geometrically. I want to be at the lower points on the surface, not at the higher point on the surface. Or I could have tracked through all of the inequalities going through here. But either way, I see that this is where I want to put the bed, kind of along that x equals 10 wall. I'd rather have the bed over on that side where it's a bit cooler and not right above the heat vent. I suppose that's kind of common sense. We maybe didn't need Calc 3 to figure out that if you want to be cool when you sleep, don't put your bed on top of the heat vent, put it on the other side of the room. But of course, you can imagine a more complex, more complicated setup where we might have a more complicated surface, taking the temperature at different points in the room with different heat vents and different heat sinks as well, different maybe windows making one area cooler or something. Any questions so far? Oops, I just realized there was a question in chat. Okay. I think I had addressed that already. Okay. So moving on then to level curves and contour maps, we've kind of hinted at this idea already when we were looking at this temperature equals 70 plane and seeing where it intersected the surface. Where does this surface have height 70? That's along this curve that looks like a circular segment. So again, I've kind of used the textbook's drawing here because it's much better than what I can do by hand. So what's the idea of a level curve? The idea of a level curve is we have some surface in 3 dimensions. We have 2 inputs and 1 output. That gives us this 3-dimensional surface. And that surface has at each point a certain height. Well, there's a collection of points. There's a curve in 3-dimensional space where along that curve we have the same height on this surface. So in this case, it looks like these are circles. So for instance, on this circle here, it seems like we have height 45 along that entire curve. So there's a circular curve in 3-dimensional space that's on this surface and also has height 45. In other words, it's kind of the intersection of the plane with height 45 with this surface. That intersection makes a circle, a circular curve. That's really what we kind of found up here. We said what we found, just saying it another way, is that this circular segment here is the level curve where t equals 70. So what can I do with these level curves. So what I could do is I could have a two-dimensional representation of this three-dimensional figure. I mean, we kind of saw up here that even for a pretty simple surface, it's kind of tough to draw it by hand in a way that looks pretty reasonable. But maybe what I could do is I could instead, I know that I can draw two-dimensional things quite well. There's not perspective to take into consideration. There's not things hidden behind other things and so on. Maybe what I can do is I can take each of these level curves for a selection of different levels, maybe 45, 40, 35, and so on. I can take each level curve, drop it down to the XY plane or to the domain, the two-dimensional plane that's the domain, and represent that curve in 2 dimensions. So I might have something like this that I would call a contour map. And I'm sure you've seen these before with, maps or something like that, where they're trying to show you where mountainous areas or valleys or something are. You might have seen contour maps like this in that setting. So what is this representing? It's representing a function f of xy. So this xy plane that we're looking at here is the domain space. These are the inputs, like we might have an input of 1, 2, or of 5, 4. And these curves, these kind of, somewhat elliptical like curves, the one that's labeled 10 here, this is the set of all inputs, xy, that would give me an output of height 10, that would give me a z equals 10 if I were graphing this in 3 dimensions. The curve that intersects the 20 is the set of all the xy points, set of all the inputs in this 2 dimensions, that would give me a height of 20, and same for the 30. So I could imagine if I kind of wanted to reconstruct my 3D picture, I could take this xy plane with these curves, I could kind of lay it flat on the desk. I could take that 10 figure, that kind of loop, and I could lift it up 10 units. I could take the 20 loop and lift it up 20 units, and the 30 and lift that loop up 30 units. And that would give me somewhat of an outline of what my function might look like, that surface might look like with the 2 inputs and the 1 output. But if I think of just smashing that all down to the xy plane to z equals 0, this would be what some of those curves would look like. Now, obviously, there's a trade-off here. The more curves that I have, in a sense, the more information I have, but also the more cluttered the picture is. So there's a bit of a trade-off here. We don't want to give a set of a contour map that has level curves at every 1 unit increment, 10, 11, 12, and so on. That's going to be just a huge blob of ink on our page. But on the other hand, if I just gave you, a level curve at 10, that's probably not super helpful for most applications. So just like if we were to choose a tabular representation of a single variable function, we'd have to make a reasonable choice of inputs and outputs to represent the function. Same idea here. Okay, but let's take this contour map, this set of 3 level curves, and try to answer these questions. For approximately what values of y is it true that f of 5, y is between 10 and 30? So here I know x is 5. And I'm asking what happens as I vary y. Y could be closer to 0 or closer to 12 or in between. For what values of y, when x is 5, is the function between 10 and 30? Well, I know that as I go this way, I'm climbing from 10 to 20 to 30. And as I go this way, I'm climbing down from 30 to 20 to 10. Oops. So it sure looks like for the set of y's that span that line whenever x is 5, from when I start at 10 on the bottom, kind of climb up to 20 and up to 30 as I'm increasing y, and then down from 30 to 20 to 10 on the other side, as I continue to increase y, it looks like that's the set of y's that would give me outputs between 10 and 30. Or maybe that would be something like y equals maybe 3, and maybe something like y equals 10, right? I mean, this is a picture, it's not going to be perfect, but something like y between 3 and 10. Can we estimate the value of f of 2 comma 4 from this picture? That might seem like a tall order. I mean, we don't even know what the surface looks like. I mean, we don't have a visual representation of the surface itself. We just have these contour maps. But what do I know about f of 2 comma 4? Here, x equals 2, y equals 4. Well, I know that point is maybe about here. Maybe actually a little bit higher, maybe about here. Well, I kind of see that in between these contour, these level curves of 10 and 20 on this contour map, that's where my point lies. It kind of lies in between those two. And it looks like it's maybe, say, in the ballpark of halfway between the two. So with my input being, say, maybe in the ballpark of halfway between, say, two inputs on these two level curves, maybe I would expect my output to maybe roughly be in the ballpark of halfway between the outputs of those two level curves. In other words, the average of 10 and 20 may be about 15. Again, this isn't going to be a super precise estimate, but this gives us, a ballpark anyway. So what about f of 4 comma 2? Here x equals 4, y equals 2. And there's kind of two ways that we could approach this. On one hand, we could say, well, we're kind of outside of the realm where I have really definitive numbers. In fact, I don't even know if 4 comma 2 is even in my domain. Right? If I knew that I had a point that was between the level curves for 10 and 20, I mean, I suppose it's theoretically possible that I have a hole in there or something, but I can probably make a pretty decent guess that that's going to be also filled in between the two, and that the output's going to be somewhere in between those two outputs. But something like 4 comma 2, I mean, I guess strictly speaking, I'm not so sure. So on one hand, I could say, well, I can't really estimate 4 comma 2, the output of 4 comma 2 with as high a degree of certainty as I could estimate the output associated with the input of 2 comma 4. On the other hand, if you were kind of forced to make an estimate, you might look at this and say something like, well, kind of in this direction, the level curve going from 20 to 10 spans about that distance, and this point may be about the same distance away from 10 as 10 seems to be away from 20. Maybe I would guess 0. So I might guess 0, or I might say we can't really reliably do it. Again, anytime that we're making an estimate or approximation, there's some amount of allowance that needs to be made. So, how important is it that we get this right? If it's a life and death situation, I probably wouldn't want to make the estimate here. I want more information. If I'm just looking for a ballpark number, can I maybe guess the output might be around 0? Maybe. But kind of as a side note, this hints at a bigger idea. There's the idea of interpolation. In other words, I have some firm data, and then I'm making an estimate of a data point that kind of lies within that data. That would be something like this. I can usually make such estimates with a much higher degree of certainty than extrapolation, where I'm kind of going outside of the data that I have into kind of unknown territory and trying to make an estimate there. So kind of as a general rule across applied math and statistics and fields that use applied math, interpolation is much more reliable than extrapolation. But again, I might either say, I don't feel comfortable making that estimate because heck, I don't even know if the thing's in the domain of the function. Or I might say, 20 to 10, and the 20 to 10 curve seems to be about as far away as the point is from the 10 curve. So yeah, maybe I think that it goes down another 10 or so in that same distance. Of course, all of this is fairly hand wavy, right? Okay, so part D. How many values of y satisfy f of 7 comma y equals 20? So when x equals 7, how many values of y give an output of 20? Well, when x equals 7, I can actually think of this just being like f of y equals 20, right? I can actually think of this being like a one variable function with the input of just y. What height are we at over here, indicating where are we at over here, and then what is the associated output? When is such an output equal to 20? Well, that seems to be just at this point and at this point. So there are two values of y that satisfy f of 7 comma y equals 20, and it seems like, oh, maybe they're around, say, 9 or so. And maybe around, say, 3 or so. Let's say 9. There. And then a similar question, how many values of x satisfy f of x comma 9 equals 20? So again, I can think if I fix y to be 9, I'm only looking at inputs that fall along this straight line here, this red line. This is the red line associated with y equals 9, or the straight line associated with y equals 9. And I see it kind of looks like, so I'm asking when is the output for a given input x equal to 20? Well, it looks like 1, remember this 20 level curve is the one in the middle here. So 1, 2, 3, 4 maybe. So it looks like about 4. Looks like there are 4 values of x that satisfy f of x comma 9 equals 20. And that might be something like 2, 3.5, 7. Well, we kind of found the 7 up here, I think, already. And 9. So more or less those 4 values for x look like where we would have f of 2 comma 9 being about 20, or f of 9 comma 9 being about 20. But there, it looks like there are 4 values of x that satisfy this relationship, whereas there are 2 values of y that satisfy this relationship. Are there any questions so far? Okay, so a little note here, the contour map of a linear function, a plane, z equals ax plus by plus d, and we'll take our contours, let's say at the integers, at evenly spaced points, we'll just take the integers for instance, consists of equally spaced parallel lines. This is pretty simple to show. I'll leave it as an exercise. So as an exercise, try to show that, try to show very clearly, like as if you're writing up a proof, not hand wavy, that this is a true statement. Okay, let's take a look then at functions of 3 or more variables. So for each of these functions, let's sketch the domain. So for A, let me get a little more space here. For A, we have square root of 16 minus r squared s squared t squared. And we know that we need our inputs into square root to be greater than or equal to 0. Well, this means that r times s times t squared has to be bigger than or equal to 4, or this means that -4 has to be less than or equal to RST has to be less than or equal to +4. That's the algebraic or algebraic restriction on our domain. Note that our domain here is actually 3 variables. So we're switching gears here. For a function of 3 variables, our domain is a region in 3-dimensional space. Put an exclamation point there. So what we're going to draw here is not a representation of the function. It's just the representation of the allowable inputs. Very important. Up here, when we drew a 3-dimensional picture, this was a representation of the function, our 2 dimensions of inputs and 1 dimension of output. Here, when we draw a 3-dimensional picture for a function of 3 variables, this is just representing the allowable inputs. And then we would have a separate real line over here that these are getting mapped to. I do notice that I have a decent bit of symmetry here. In other words, R, S, and T all kind of act the same way. So if I didn't have one of those, if I just had something like R, S is between -4 and 4. Yes, yeah, thank you. I have an extra vestigial squared over here. I didn't carry it over to my final bit, but yes, this should be just RST bigger than or equal to 4. Oh, I actually do need the squared there, and I need a squared here. That was I needed a squared there. Yeah, thank you for pointing that out, though. Yeah, it's RST squared bigger than or equal to 4 squared. And then when we square root both sides, obviously we take plus or minus. That's where we get RST between -4 and +4. Yeah, thank you for pointing that out. I needed this squared on the 4 still at that point. If I imagine what kind of the 2-dimensional analog of this would look like, I have a lot of symmetry here, and there's kind of a saying in math and some other technical fields like physics and things like that, that when there's symmetry in a problem, if you respect that symmetry, it often rewards you. So what would it look like to say RS is less than or equal to 4? Well, that's like R is less than S over 4, S is less than R over 4. That's just this kind of a deal. And then we just have the inverse, RS bigger than -4. Right? This looks kind of like S equals 4 over R, or more or less like S equals 1 over R. And a number or a point like 0, 0, I see would be in the domain. So I'm looking at points that are kind of within this star shape. Now, this isn't my full answer here. This would be kind of like the answer. This would be like the cross section with, say, T equals 1 is what we'd be kind of looking at here. But I can actually see pretty clearly that this idea is going to carry over. I'm going to have, and it's going to be pretty hard for me to draw it in a way that I think is convincing, but I'm going to have what basically looks like a star shape where I have a point of the star going in the direction of each of the positive and negative axes. So I have basically, if you imagine this thing, but kind of going up and down, left and right, but also forwards and backwards. So the kind of interior of this volume here, the kind of it's kind of like 8 poles or 6 poles in a sense, kind of going in each direction. maybe looks a little bit like one of those like jacks, if you ever played like balls and jacks and stuff. Something along those lines. So the interior of that volume is going to be our domain. These are going to be the points that we can plug into this function. And then the outputs would be mapped to another real line. This is our outputs. Or this is where our range would live over here on the red real line. Okay, so looking at this example, I'm going to give the answer here, but I'm going to leave it as an exercise to work out the details. Just to make sure that we do have a chance to get a decent start on partial derivatives. But the answer here is going to be a plane that intersects the x-axis that's elevated 45 degrees. So the intersection with the zy plane when x equals 0, z equals negative y, and in fact, z equals negative y for any fixed value of x. We're looking for a three-dimensional region to define our domain. It's going to be anything above this plane, anything with a higher z value than we see in this plane. But we have to be careful. X cannot be 0. So we have to exclude. And since I'm never going to be able to draw this, I'm just going to write over here, excluding the YZ plane. So x equals 0 is the YZ plane. We do not want to allow x equals 0. But this 45-degree plane that cuts through x and is 45 degree in the YZ direction, anything on that plane or above it, as long as x isn't 0, as long as we're not in the YZ plane itself, would be a valid part of our domain. And again, this is the domain. And our outputs would be like taking points in this three-dimensional space and mapping them over here to a real line. So for a function of 3 variables with 3 inputs, we can't really draw a three-dimensional surface that represents this function well, right? Because the 3 dimensions are all taken up just with the domain, just with the inputs. So how can we represent such a function? And here's one example. We can try to draw a set of level surfaces. We can try to draw a set of, remember our contour map above. This was taking a 3-dimensional idea, 2 dimensions for the domain, 1 dimension for the output, and pushing it down into the domain and drawing curves in the domain that are level curves. Well, now we have a 3-dimensional domain. So the domain consists of some surfaces, and we're trying to find level surfaces. We're trying to ask when, for my function of 3 variables or 3 inputs, when is that output constant? Over which surfaces is that output a constant number? Drawing several such surfaces and labeling each of them with their value, with their output. So something like this, for instance, for the function x squared plus y squared plus z squared, my inputs are x, y, z, and my outputs could be, for instance, 1 or 4 or 9. So what would be the level surface? What would be the surface where all of the inputs on that surface give an output of 1, well, that's going to be my sphere radius 1, this kind of pink ball in the middle here. What's going to be the surface in 3 dimensions where my outputs are all 4? Well, that's going to be the sphere of radius 2, this yellow ball here, and similarly for outputs of 9, sphere of radius 3, the blue ball on the outside. I mean, again, you can see for even a fairly easy function to understand, good luck trying to draw that by hand unless you're a very, very good artist and make it at all convincing. Okay, any questions on 14.1? All right, so again, we're going to skip over 14.2 for now. That'll be a supplement. Moving on to 14.3, we're going to get a start on partial derivatives and then wrap this up in Wednesday's class. We're going to start with a motivating application. And the idea we'll look at is the heat index, kind of a similar idea to wind chill, but for heat. So heat index is a function of temperature, just the kind of, if you had a thermometer, what temperature is it, but also the relative humidity H. So how hot does it feel to us? Well, that depends on the temperature and the humidity whenever it's warm outside. And when it's cold outside, how cold does it feel to us? That depends on the temperature as well as the wind. We note that changing either T or H, either of these two inputs, or both, will result in a change of the heat index. We might be interested in this idea of what's the marginal effect of a change in one of the independent variables on the dependent variable. In other words, suppose that outside and it's currently 96 degrees with a relative humidity of 70%. If it were to get in the heat index from below, from this chart, temperature 96, relative humidity 70%, heat index is 125 degrees. So somebody said somewhere that it feels like 125 degrees when it's this humid at this temperature. Well, what if the temperature stayed the same, but the humidity got a little bit more humid, say increases by 1 percentage point up to 71%? Can we estimate the change in the heat index? I mean, I don't have 96,71 here, but can I estimate how the heat index will change when I keep the temperature the same, but change humidity by, say, 1 percentage point? Or in other words, if delta H was 1 and delta T was 0, if temperature stays the same, what do we think delta I would be? How does delta I relate to delta H for a constant temperature? Or similarly, if the humidity were the same, but the temperature changes, if the temperature increases by 1 degree in that same setting, but the relative humidity stays the same, how would the heat index change? What would I estimate delta I as if I knew delta T was 1 and the relative humidity did not change? So let's take a look here. Maybe I'm going to delete a few of these spaces just for the time being. So what I'm interested in is how does delta I change, or what is my new heat index? So I plus delta I is F of the temperature was 96, that stays the same. And here I have H plus delta H. How do these relate to one another? Well, I notice that I'm really only changing one variable, right? If I'm really only changing one of these two variables and the other one is being held constant, I mean, if we go all the way back up here, that's a little bit like, say, moving along one of these red curves when, say, I was changing y and holding x constant. I mean, that's kind of just like a Calc 1 question, right? So what could I do? Well, maybe what I could look at is I could say, look at a couple of different relative humidity points for a temperature of 96. In other words, I see, for instance, that f of 96 comma 65 is 121, and f of 96 comma 75 is 130, right? Just getting these two numbers. I'm moving along the humidity direction, but staying fixed in the temperature side of things. Well, I noticed that f of 96 comma 75 minus f of 96 comma 65, the change in the outputs over the change in the inputs, just with respect to h's input is changing, like 75 minus 65. That's what, 130 minus 121 over 10, or that's 0.9. This seems like an estimate of delta I over delta H, right? The change in the output over the change in the input when temperature is held constant. So it seems like 1 percentage point increase in the relative humidity would be associated with a 0.9 degree increase in the heat index. So if we went from 70 to 71% and kept that 96 degrees the same, I might estimate that I of 96,71, where this is increased by 1 percentage point, is what, 125 plus 0.9 times 1, right? This is delta H equals 1. That's where this comes from, right? Just a linear approximation. This is just calc 1, because that 96 is not changing at all. We're just moving in one dimension. We're just moving in one variable. Or this would end up being 125.9. And this is, of course, an approximation, a linear approximation. We could do the same thing if we looked at changing temperature. Let me just erase all of this and then move this graph back down. So again, if I looked at changing temperature, what am I looking at there? Well, here I'm saying I plus delta I is related to f of, well, what's this going to be? 96 plus delta T, comma 70. So here I'm setting H equals 70. I'm staying in this 70 column, but now I'm varying temperature. And as an aside, why did I go from 65 to 75 instead of 70 to 75? Just as an aside over here, in case you kind of forgot the idea from Calc 1, if I'm looking for an estimate of the slope of the tangent line, I could go to one side, but that's going to give me kind of either an overestimate, or if I went to the other side, an underestimate. But if I use a secant, if I go a little bit to either side, I get a better approximation. This is actually a provably better approximation. It's a second order rather than first order approximation. So that's the reason why I went a little bit to the left and a little bit to the right, so to speak. I went down a bit and up a bit to make my approximation. Could you have done it just going 70 to 75 and making an approximation that way? Sure. Or 65 to 70? Sure. Again, once we get into estimating things, there's lots of ways to skin that cat. But now that we're talking about changing the temperature, we're fixing the humidity at 70%. If the humidity stays the same and temperature wiggles a little bit, what effect does that have on the heat index? how does changing that input a bit change the output? But again, I see that f of 98 comma 70 equals 133, and f of 96 is our kind of anchor point. So f of 94 comma 70 going down a little bit is 118. So what do I have? Well, I have that f of 98 comma 70 minus f of 94 comma 70. Sorry, I just had something random pop up on my screen and I wasn't sure why. But anyway, f of 9870 minus f of 9470 over 98 minus 94. This is the change in the heat index over the change in temperature. This is di dt. I'm not sure if somebody's like writing on my screen. I don't know why Zoom would allow that to happen, but if you're writing on my screen or something, or annotating or something, oh yeah, disable annotation. Okay, I didn't know that was an option. So, but anyway, so we have delta I over delta t is approximately, and what is this? 133 minus 118 over 98 minus 94. So what is that? 15 over 4, or what's that? 3.75. And again, so I plus, or let's say I at 97 comma 70, if the temperature increases by 1, is approximately I of 97 plus delta I over delta t times delta t, or sorry, I of 96 so I of 96 was 125 plus 3.75 times 1. So 128.75. So if the temperature increases from 96 to 97 and the humidity stays the same at 70, we approximate the new heat index as 128.75. Okay. Any questions on that? Give me 1 second here. Okay. Yeah, I didn't realize the annotations were a thing, so I found a way to turn them off and to remove the one that was on there. So I think we are good now. Okay, but the main point that I want to make up here is that if we hold one of the input variables fixed and vary the other one, that acts a lot like a one-dimensional function, that we can do things like, for instance, linear approximation like we did in one dimension. This should all look very familiar from Calc 1. So that's the motivating idea. So what about partial derivatives then? What are partial derivatives? Well, here we again have two inputs. So if we're thinking of a derivative, we want to say vary the inputs. Or in this case, we want to vary just one input at a time. right? In a single variable function, we would vary the only input and see how that affects the output. In a multivariable function, we really don't want to vary both inputs at the same time, say f of x plus h, y plus k or something, minus f of x, y. Well, now I'm moving in the x direction as well as the y direction. How does all of that come together? I'm not completely sure yet, but I know that if I say hold y constant and vary x, if I look at f of x plus h minus f of x over h, when y is constant, it's not really acting as a variable here. That idea f of x plus h minus f of x over h is really just like a derivative in Calc 1, but where y is just being held constant. So what am I effectively doing? Pretending in this case that x is a variable and y is a constant, and I'm just treating this like f of x plus h minus f of x over h, and y is just kind of coming along for the ride. Or the other way that I could look at it, instead of holding the second variable constant and changing the first, I could hold the first variable constant and change the second. I could look at this kind of as f of y plus h minus f of y over h. If I'm holding x constant, it's just kind of coming along for the ride, right? Again, I'm going to run up to this picture we had up here because I think it's a decent enough picture and I don't want to have to draw it again. I could imagine, say, holding x constant, say here, and varying y. And when I do that, I basically just have a one-to-one function, one real input, one real output, relating, say, y to z. Or I could hold y constant, vary x, and then again, I have kind of a one-to-one or a one input, one output function, in this case relating x to z. So that's the idea down here with partial derivatives. These are partial derivatives because we note that when we're varying x and holding y constant, we're really only getting an idea of the contribution to changes in x to the change in the overall function height, and we don't really know how y is coming into play. And when we're varying y but keeping x constant, just the opposite. We're getting some information about how changing y changes the output, but we really don't know anything about how changing x changes the output. So these are partial derivatives in the sense that we get a part of the whole information about how the change in inputs changes the output from the x partial derivative, and we get part of the information from the y partial. And as I kind of mentioned before, the partial derivatives basically just act like standard Calc 1 derivatives, where if we're taking the x partial, we just basically pretend that y is a constant and just comes along for the ride. And vice versa, when we're taking the y partial, we pretend that x is just a constant coming along for the ride and that y is the variable that we're differentiating with respect to. So what's some notation? There are a bunch of different ways to denote partial derivatives. Probably the most common is just f sub x, for instance, for the x partial of f. We could be a little more explicit about the coordinate that we're inputting, fx of x comma y. We have this notation that looks kind of similar to, it's kind of like a df dx, but note that it's a curly d. It's not df dx, it's curly df curly x. It usually just said partial f partial x, but these are curly d's. And this is actually an important distinction. It's not just a notation level distinction, it is actually an important distinction, and we'll talk about that a bit later in the course. But because these are partial derivatives, they don't kind of have all of the information that like a df/dx would have about how changing the inputs overall affects the output. This only has kind of part of the information. So this is actually a deeper difference than just a notational consideration. We could think of the differential operator like this, partial by partial x of, say, f of xy, or d sub x applied to f. And an important note is that the subscript x simply, so this x in the bottom here, like f sub x, simply indicates that the derivative is with respect to the first independent variable, and the x inside the function, the x comma y for the coordinate for the argument, is just naming that coordinate. We could just as well say f sub 1 of xy to indicate that we're differentiating with respect to the first argument instead of fx of xy. And, this might even be, strictly speaking, better notation or more accurate notation because we're not using x in two different ways as we are here. So we have to be careful about that. That's actually a nuance that I really did not appreciate until into grad school when you look at a topic called calculus of variations, it pops up, and it's actually an important distinction. So we'll see a little bit more on that later on. But for our example here, which will probably take us to the end of class, we will compute the partial derivatives with respect to x and y for each of these three functions. And then if we have time, we'll evaluate them at the coordinate 1, 2. So here I have a function f of x comma y is just this polynomial function, 2x squared minus 3xy plus 4y cubed. So what is fx, f sub x, or the partial of f with respect to x? Again, remember the mindset that I have here. When I see that I'm taking the partial with respect to x, x I'm thinking of as the variable, and y I'm just thinking of as a constant. I could just as easily replace y with a number like 3 or something like that, and I would get a very similar result. So 2x squared, I don't see any y's there. I know how to differentiate this. That's just 4x. Minus 3xy. Well, what is this really? This is like minus 3y times x. Remember, this is just a constant. If I have constant times x, that differentiates to just constant. Minus 3y times x, that minus 3y is all considered a constant. Constant times x, differentiate that with respect to x, I just get the constant in front of the x back, that's minus 3y. What is 4y cubed with respect to x? Well, that's just a constant. It's nothing fundamentally more different than, say, 12 or something like that. If I differentiate 12 with respect to x, what does that give me? That just gives me a 0. If I differentiate 4y cubed with respect to x, that's just a constant. Differentiate with respect to x, this gives me 0. Or, of course, I would typically just not write that term. So what's the f dy, the partial of f with respect to y? Now I have to switch my thinking a little bit. I am thinking of the x's as being constants and the y's as being the variable that I'm interested in. So 2x squared, this doesn't have any y's in it. As far as y is concerned, it's a constant. If I vary y, the value of 2x squared doesn't change at all. So the derivative with respect to y is 0. For df dy, minus 3xy has a constant, minus 3x, times the variable y to the first power. If I differentiate constant times y with respect to y, I just get constant. I just get minus 3x. Note that we got minus 3x for df dy and minus 3y for df dx. Slightly different outcomes for those terms. And now df dy, now 4y cubed, I don't see any x's. This is just a very straightforward derivative. 4y cubed df dy is plus 12y squared. This seems very strange the first 2 or 3 times you do it, and then it kind of clicks and you're just like, oh, okay, this is actually really easy. Okay, so what about this function? F of xy equals sine of x squared plus y divided by x minus y. What's the f dx? Well, here I have a function of x over a function of x. I have to use the quotient rule. So I have a bunch of stuff over the bottom squared. And I have bottom derivative of top. So d by, whoops. I'll write the bottom first, bottom, d by dx, derivative of top, minus top, partial with respect to x, of bottom, x minus y. My product rule, quotient rule, chain rule, all work exactly the same under that constraint that when I'm taking the f dx, the partial f with respect to x, I think of x as the variable, y as a constant. Or this gives me x minus y over x minus y squared. Let me come back to this one. But we have some stuff, minus sine of x squared plus y. And then what's d by dx, partial with respect to x, of x minus y? Remember, this is a constant. That differentiates off. D by dx of x is just 1. So this whole bit just equals 1. So this is just times 1, or we don't have to write that 1 if we don't want to. And then lastly, what about partial with respect to x of sine of x squared plus y, where I have a function of x. So the derivative of sine is cos x squared plus y times partial with respect to x of x squared plus y. This constant differentiates off, and this just gives me 2x. I might be able to simplify this a bit, but it's not going to get me very far. I suppose I could knock this factor of 1 off the end there, but that's about the nicest I can make it look. And then df dy, it's going to be pretty similar. We're still going to get an over x minus y squared. We still get an x minus y in the top. Note that as far as the denominator is concerned, x and y work pretty similarly, right? The numerator is a little bit different. I'm going to have x minus y dy, partial with respect to y, of sine of x squared plus y. But that's cos x squared plus y times partial with respect to y of x squared plus y. That's 0 plus 1 when I take the partial with respect to y, treating x as a constant. So I just get another factor of 1 out here from the chain rule, or I don't need to write it, minus top times the partial with respect to y of the bottom. The partial with respect to y is going to be 0 minus 1, or that's a minus 1. I can just switch that sign. That's from the minus 1 factor, switches that sign. And again, that's probably about the best I can do, other than maybe getting rid of that little factor of 1 inside of there. Okay, so that takes us to the end of class today. Let me stop the recording.